Hello everyone, I want to welcome you to another section. This section will be the third video on how to read higher spectrum. At the same time, this video will also be the last video, or let me say lesson, on how to read higher spectrum. So, in the previous video, we were able to look at how to read higher spectrum in order to be able to identify whether the spectrum contains saturated compound or an unsaturated compound. In the second video, we were also able to know how to read spectra that represent, or let me say that identifies carbonyl compound, which can be an aldehyde, a ketone, a carboxylic acid, an ester, acid anhydride, or an imine. We highlight some of the signals we can always look out for in the IR spectrum in order to identify what class of compound the IR spectrum tries to represent. In this video, I've given us the completing part of signals that we have to look out for some other compounds apart from saturated and unsaturated compounds, at the same time apart from carbonyl compounds. At the end of this video, we are going to be looking at these IR spectra and we're going to be using the given values to elucidate what class of compound the each of the IR spectrum might simply represent. So we've talked about how to know whether the compound represented by your IR spectrum is saturated or unsaturated by checking for signals around 3000. We also talk about the fact that for carbonyl compounds, the signal for carbonyl compounds always falls between 17 and 18. But in some cases, due to conjugation or mesmeric effect, they can also fall a little bit below 1700. I will try to give us some diagnostic signal that can be used to differentiate different carbonyls from one another. In this video, I'm going to be giving us signal that we can always use to identify alcohols. So alcohols compound usually contains your OH bond. So the OH bond in alcohol is different from the one that you have in what do I call it, in carboxylic acid. The one in carboxylic acid is usually involved in hydrogen bonding, but in most cases the OH group in alcohol is always a free OH, not particularly hydrogen bonded. So for free OH group in any compound, the signal is usually a broad signal at around 3300, but without spikes. If you remember when I was talking about amine, I said one of the signals by which you can identify your amine is the NH2 stretching vibration, which is a broad signal at around 3003 with spikes. But for free OH functional group, the signal for free OH is usually at around that same place, but it's usually broad without spikes. So when you have a broad signal far above 3000, and I've said spike specifically at 3300, and it's without spikes, it means you're having a free OH functional group in a given compound. Another part of compound I also want to mention is cyanide or your nitriles. So for nitriles are compound that usually contain C triple bond N. So in all nitrile compound, you always have your C triple bond N. So the signal for C triple bond N is like a diagnostic signal to identify spectra that represent your cyanide or your nitriles. So the sharp signal at 2200 represents the C triple bond N stretching vibration that you only have in nitriles compound, or let's say the cyanide. Now another class of compounds that we also want to look at that your higher spectrum can also represent is what we call the imines. Imines are compound with C double bond N. Imines they are actually compound with C double bond N. And so in a way, one way to identify imine compound is when you have a signal that represents your C, that represents C double bond N. And the signal for C double bond N stretching vibration is usually found around 1660. So I said the signal at 1660 that is very sharp can be used to identify imines. So and I said this signal is for what? For C double bond N stretching vibration. So that's what this represents. This one is for what? It's for C triple bond N. That's what this one signifies. Why this I've said is for what? It's for free OH group. Last type of compound that with our higher spectrum can also represent is what? Is the amines. Amines, which is RNH2. Now, amines will usually contain your broad signal for NH2 stretching vibration. So a broad signal with spikes around 3,300 will certainly represent the NH2 that can be found in amine or at the same time can be found in amide. But the major difference between your amine and the amide is that you are going to, one has carbonized signal, one do not have carbonized signal. So it implies that if I see a signal around 3,300 which is broad and with spikes, but I could not see a signal for carbonyl functional group. So that should tell us that it will be the compound represented by the higher spectrum will be an amine. So a signal that has a spectrum that has NH2 stretching vibration but do not have a carbonyl signal will simply represent your amine. And these are other signals that I want to mention that can also be useful in reading your IR spectrum. And the signals I've mentioned in this video and the ones I've mentioned in the previous first and second video are enough for you to be able to read your IR spectra correctly. But like I said, that in this video we are going to work on some examples to see how to always apply some of the things that we have learned. So now we are going to be looking at these different IR spectra 1, 2 to 6. We are going to be looking at them and we are going to be identifying what compound each of them represent, or let me say the compound they represent and the functional group that is present in them. So starting with the first one, we have a signal. Again, that we have a signal between 3,350 and 3,200, which is broad. B means broad, and it is with spikes. At the same time, we also have a signal between 2,980 to 2,850, which is just below 3,000. At the same time, we have a signal around 1,701 and what's it called, and 1,660. Now the question is, what does this represent? What compound does this spectrum represent? Now, from what I have said so far, the first thing that should come to our mind is the signal around 3,000. So this signal we have around 3,000 is just below 3,000, which means that what we have saturated compound, that is your sp3 carbon, within the compound represented by this IR spectrum. At the same time, we don't have any signal just above 3,000, which means that the compound do not contain unsaturated carbon. So it means that this compound represented by this spectrum is a saturated compound. So what that is, can we see there? We see a signal between around at 1,007 and 1,660. Now this signal that we have there is certainly for what? For carbonyl signal, because I told us that carbonyl signal can be found between 1718. But in some cases it can always fall a little bit below that particular region for probably conjugation reason or Mesmeric effect reason. So at the same time, we also have a signal between around 3,350 and 3,200. It's a broad signal with spikes, and from what I had said earlier, a broad signal around 3,003 with spikes represents your NH2 stretching vibration. So with carbonyl signal NH2 and this signal for saturated carbons, we can conclude by saying that this spectrum represents a saturated amide compound, because it's having a carbonyl signal, it's having an NH2 stretching vibration, and it's having a signal just below 3,000. So the first spectrum that we are looking at here is a spectrum for a saturated amide compound. In the second spectrum now, we also have a signal just below 3,000, which is between 2,970 and 2,830. So this is a signal just below 3000, which also implies we are having a saturated carbon within that compound. We also have a signal a bit above 3000, which is 3020. So this signal here represents your sp2ch, which you can always find in you can find them in unsaturated compound as alkenes and also your aromatic compound. But we also mentioned that if you see a signal just above 3000, you also have to determine whether the sp2ch is in an aromatic system or whether it is in an alkene. And what makes the difference between those two is the signal at 1600. If you have a signal at exactly 16, it means that the sp2ch that you have is in an aromatic system, an aromatic ring. But if you have it a bit above 1006, it means that the sp2ch signal that you have here is for an alkane. So here we are having a signal just below 3000, we are having a signal just above 3000, and we are having a signal above 1006. So that means that this compound is an alkane. So this compound is an alkane. We said this one is an amide, saturated one, saturated. So for the next spectrum that we have here, we also have a signal just below 3000, which represents your saturated carbon being within the IR spectrum. We also have a value a signal at 1710. Now, a signal at 1710 means that the spectrum is for a carbonyl signal. But now that we know that we have a signal just below 3000, we have a signal for carbonyl functional group. Yes. So the question is, which class of carbonyl does this particularly represent? So because of this signal that we have here, which is a broad signal around 3000, from 3001 to 2008, it's a very broad signal. So that signal that we have is specifically found in carboxylic acid. So from the third spectrum that we have here, we have a signal just below 3000, we have a carbonyl signal, and we have a broad spectrum around 3000. That implies that this compound is a carboxylic acid. It's for a saturated, let us forget that it's a saturated carboxylic acid. Now, it is not an unsaturated one because we don't have any signal just above 3000. Looking at this one now too, we only have a signal just below 3000 and we have a signal at 2240. Now, from what we have done in this particular video, I mentioned that generally when you see a signal at 2200, that is for what? Is for your C triple bond N stretching vibration, which is usually found in nitriles or your cyanides. So that means, with this signal just below 3000, which represents your saturated carbon, and the signal at 2240, which represents your C triple bond S stretching vibration, we can conclude by saying that this compound is a saturated cyanide. A saturated cyanide compound, because you are having a signal for C triple bond N and a signal just below 3000. Now, the next spectrum that we have, which is the fifth one, in this particular signal now, we are having three different signals were given to us. We have one just below 3000 between 2980 and 2850. We have one at 2712 and we have one at 1710. Now, the signal at this 1710 already tells us that the spectrum is for a carbonyl compound. But the question is, which kind of carbonyl compound does this represent? So I said specifically that for aldehyde usually have a diagnostic signal at 2007 and 28. So with this signal that we have here, which is at 2712, we can conclude and say that this spectrum is for an aldehyde. At the same time, because we are only having signal just below 3000, that implies that it is a saturated aldehyde compound. So this one also is a saturated aldehyde compound. So it is a saturated aldehyde compound. One, because it's having a carbonyl functional group, it's having the diagnostic signal for aldehyde, and it's having a signal just below 3000. For the sixth spectrum that we have in these given examples, now the first thing we can see is a signal just below 3000, which represents your saturated carbon being present in the compound represented by the higher spectrum. We also have a signal just above 3000, which represents your sp2ch stretching vibration. So that means that the compound also contains a double bond. Now, but we are having a signal at exactly 1,6. So, and a signal at exactly 1,6 represents your C double bond C in an aromatic ring. So that means that this spectra that we have here is a spectra for an aromatic compound. So at the same time, we also have a signal far above 3000, which is, let's say, around 3300, between 3350 and 3200, which is broad with no spike. So this particular signal that we have here is usually for an alcohol, that is a free alcohol which is not involved in hydrogen bonding. So that means the spectrum that is given to us here contains an aromatic ring, at the same time contains a free OH functional group. And with these two features, we can conclude to say that the compound is an aromatic alcohol. So the compound that we have in this C spectrum will be an aromatic alcohol because of the signal just above 3000 and a signal at exactly 1006. At the same time, an alcohol because of a signal around 3300, which is broad and with no spikes. And this will be the end of lessons on how to read an IR spectrum. I believe if you have watched the first, second, and third video on how to read an IR, we have gained a lot of knowledge and skills on reading your IR spectrum. But if you are having challenges or questions or any comments you want to make, you can always drop it in the comment section. We do well to reply to any comments or questions in the comment section. And I want to plead with you to continue to watch our videos and share it with people that you know these lessons can also be of help to them. At the same time, don't forget to click on the subscribe button. We hope to drop more educative content for you that can help you academically on this particular channel. Thank you for watching, and don't forget to subscribe.